Hello, this is the first part of 6.2, transforming random variables. So we're going to be looking at this example. Long Beach Community College considers a student to be full-time if they're taking between 12 and 18 units. The number of units, and we're going to call those X, that a randomly selected Long Beach Community College full-time student is taking in the fall semester has the following distribution. So we can see the number of units a student takes from 12 to 18, and then these are the probabilities that a randomly selected student is taking that number of units. And then here we have a graph of it, a histogram, just showing the same thing. It's just another way of displaying the probability distribution. We have the number of units along the bottom and the probability that a student's taking that number of units. So the first thing we're going to do is find the mean and standard deviation of the distribution. This is just a review of what you already learned in 6.1. So just to remind you, this is the formula for the mean of a probability distribution, and another term for it is expected value. So we take the sum of each individual x value and multiply it by its probability. So for example, 12 times 0.25 would be the first one, and then we add all those up all the way down to 18 times 0.15 for the last one. And if we do that, we get 14.65. And now we're going to find the standard deviation. That's the square root of the sum of each individual x value minus the mean we just found, 14.65. This is missing a squared for some reason. And then times the probability, the individual probability. So for example, the first one, 12, the individual x value, minus the mean, 14.65 squared, and then times the probability that was associated with 12, which was 0.25. Then you do the next one all the way down to the last one would be 18 minus the mean, 14.65. You square that, and then times 0.15. So if we do that, we get 2.06. These formulas are on the formula sheet, and there are graphing calculator directions, and there's also some videos that were on the previous lesson for 6.1 on how to do this in your graphing calculator. So now we want to know, it says at Long Beach Community College, the tuition for full-time students is $50 per unit. That is, if T equals the tuition charge for a randomly selected full-time student, that T equals 50 times X. So in other words, we're taking the number of units that a student could take and then multiplying it by how much it costs per unit, which is $50. So if I just go back real quick, 12 times $50 per unit. If there's 12 units, that's how we're getting 600 here. Or 13 times 50, we get 650. And then the probabilities are still the same. So here's our graph. I want to compare it to the previous graph where we had the number of units along the bottom, and now we've multiplied all those number of units times 50. So you can see the graph pretty much looks the same. It has the same shape. It's just that all these values along the bottom are now representing the tuition. So they all got multiplied by 50. Okay, we're going to do the same thing. We're going to find the mean and the standard deviation. So I'll just go ahead and give that to you, that the mean is now 732.5. And the standard deviation is $103. So this is of this new distribution. So what did the effect of multiplying x by a constant, in this case we multiplied all the x values by 50, have on the shape, the center, and the spread of the distribution? So the shape, if we look at the graph, is just the same as the last graph. The center, let's compare the centers and spreads. So here was the old center and the old spread, the old mean and the old standard deviation. So I'm going to give you a second to think about, compare that to the new mean and the new standard deviation, and try to see if you can figure out how they changed. So maybe pause the video, think about it, try to figure it out, and then play the video when you want to know. Okay, so basically if you take the old mean and multiply it by 50, you get the new mean. So we really didn't even have to calculate what the new mean would be if we had the old mean before. We just had the tuition, the number of units, 12, 13, 14, all the way up to 18, took that old mean of that distribution and multiplied it by 50, we would have gotten this new mean. Same thing for the standard deviation. If we took 2.06 and multiplied it by 50, we get this new mean, which is 103. Okay, let's try another one. In addition to tuition charges, each full-time student in Long Beach Community College is assessed student fees of $100 per semester. So this is like a flat $100 each student would be charged. If C is the overall cost for a randomly selected full-time student, C equals 100 plus T, and then here's the probability distribution for C and a histogram of the probability distribution. So now we're basically taking the last values, so I'll go back to the old table, 600, and now we're adding 100 to those values. So now we get 700. Or for example, the next one was 650, now 750. All the way up to the last value was 900. If we add 100, we get 1,000. Probabilities are still the same for each one. And we can look at our graph. Now the values along the x-axis are 700 to 1,000, and actually I should call this the c-axis because we're calling this new variable c. So if we compare that to the last graph, the shape didn't change, still the same. Now we're going to find this new mean and standard deviation. Our new mean of this probability distribution is 832.5, and the standard deviation is 103. So now we want to do the same thing. What did the effect of adding a constant to x have on the shape, center, and spread? So this time we added $100. Last time we multiplied by 50. This time we're adding a value, and we want to see how that, what effect that has on our new mean and our new standard deviation. So the shape, again, didn't change. The shape of the distribution is still the same. What about the center and spread? So here's the mean and standard deviation, the center and spread from the last problem, was 732.5 for the mean, and now it's 832.5. And the old standard deviation was 103 from the last problem, now it's still 103. So take a second to think about how we could have calculated this new mean and standard deviation using the old mean and the old standard deviation. So what we did with the old one was basically just add $100, and we could have gotten our new mean and our new standard deviation. So we added $100 to each of the values, and instead of recalculating everything, we could have just taken the previous mean and added $100. But what about the standard deviation? That didn't change, it stayed the same. So when we added a value to each of our outcomes, we added $100. It didn't change the spread. It didn't change the standard deviation at all. So here's a summary, and this is on page 366. If you're multiplying or dividing, because that's like a form of multiplication, each value of a random variable by a number b, it multiplies or divides the measures of center and location. So for example, the mean, the median, the quartiles, the percentiles, those are different measures of center or location by b. So those will all be new values. They'll be multiplied by b. It also multiplies or divides measures of spread, so the range, the IQR, the standard deviation, those will be multiplied by the absolute value of b. The reason it's absolute value is if we're multiplying by a negative number, think of the types of numbers we get for range, IQR, standard deviation. Those are always positive values. They're positive measurements. They can't be negative. So even if we were to multiply by a negative number, our new measures of spread would still be positive. We would multiply by the absolute value of whatever number we're multiplying by. And the shape doesn't change. If we're adding the same number, we'll call A, and that could be a negative number, so it would be like if we were subtracting a number to each value of a random variable. It adds A. We can just add A to the measures of center and location, so the mean, median, quartiles, percentiles. If we want the new mean, for example, we just add A to the old mean, to the original one. But the measures of spread do not change. And the shape also does not change. We can do multiple, these are called transformations, and we can do multiple ones at the same time. So let's say we're maybe multiplying by something and adding a value. So to get our new distribution, we'll call y. If we're multiplying the old distribution by a constant and adding a constant. This is called a linear transformation. The probability distribution of y has the same shape as the probability distribution of x. The new mean, so the mean of y, of this new probability distribution, would be you take the old mean, you multiply by b, and add a. But the old standard deviation, you just multiply by b, and if it's negative, you do the absolute value. Because again, a measure of standard deviation can't be negative. That doesn't make sense. So if you're adding a constant, you only add that to the mean. You don't add that to the standard deviation. All right, let's try a problem. In a large introductory statistics class, the distribution of x, which is the raw scores on a test, was approximately normally distributed with a mean of 7.2 and a standard deviation of 3.8. The professor decides to scale the scores by multiplying the raw scores by 4 and adding 10. So they're going to get new scores. It says we're going to call those y. Define the variable y to be the scaled score of a randomly selected student. So again, they're taking all the old scores, the original scores, which had a mean of 17.2 and a standard deviation of 3.8. They're taking all of those old scores and they're multiplying each score by 4 and they're adding 10. We want to find the mean and standard deviation of y, the new scores. Go ahead and pause and try this on your own, and then press play, and you can see the answer. And then also you can try the second question. What is the probability that a randomly selected student has a scaled score of greater than 90? Okay, so to find the new mean, you're going to take the old mean. We want to find the new mean of the new scores. You're going to take the old mean of the old scores, multiply them by 4, and add 10. And we're going to get 78.8. To find the new standard deviation, remember we don't add to a standard deviation. It doesn't change the standard deviation. So all we're going to do is take the old standard deviation and multiply by 4. And you get 15.2. So now we want to find the probability that a randomly selected student has a scaled test score greater than 90. If we go back, it says there was a normal distribution. X was normally distributed. So the original scores were normally distributed. And if we did a linear transformation, the new scores, the transformed scores, are going to have the same shape. They're going to be also normally distributed. So we can use a normal distribution. Basically what we're doing is the distribution is normal, so I have my normal curve. The mean, the new mean of this distribution is 78.8, so here's 78.8 in the middle, and we want to find the probability a student scored 90, greater than 90. So here's 90, and then I went ahead and shaded greater than. So we're basically finding this, the probability that a randomly selected student has a scaled test score, those are the y, the new test score greater than I put or equal to, but really it's the same thing when we use a normal distribution, greater than 90. So we find a z-score, which is the value minus the mean over the standard deviation. We get 0.74. And then we want to find the shaded area. You're going to go to normal CDF. We're going to do 0.74 as the lower bound, and then just a big number for the upper bound, and we should get 0.2306. So about 23% is the probability that a randomly selected student has a scaled test score greater than 90.